Hello everyone. So in this video I'm going to show a basic skills that I think you guys need to know whenever you face a resonance problem. So I hope by following these steps, and once again in the video what I'm going to do is using an example, I'm going to show you the steps that you guys need to follow whenever you face a resonance problem, which you can apply to the online homework that I have already uploaded on Clutch Prep. Okay, so here is a molecule. In this case, it's a positively charged ion, carbocation. The positive charge is on this carbon. And the question here could be draw all the potential resonance structures that account for the real structure of this ion. So whenever you see a molecule from now on, doesn't matter if it is an ion, in this case a carbocation, a carbon ion, or a neutral molecule. First question that you need to ask from now on is this a delocalized system? That's the first question that you're gonna ask. The reason for that is if it is a delocalized system, then obviously now you know that a single Lewis structure will not be good enough to explain the real structure of this molecular ion. That is the whole point of resonance theory, right? In delocalized systems, a single Lewis structure is not enough. So we need to provide several of them. That's what resonance is for. And then to answer this question, the first thing that we need to do is and that's going to be your first step, it's going to be to assign hybridization to every atom in the molecule or ion. Okay? That's going to help you to answer this question properly. So I'm going to assign the red color, and in this case, for you guys to see better, I'm going to say red equal sp2, blue equals sp3 hybridization. Okay, there's no any sp hybridized atom because I don't see any triple bonds. Okay, so I'm gonna start by the carbons. Okay, and I'm gonna say that this carbon over here, I'm gonna assign the red color to this carbon because in that carbon you can see how there is a double bond. Whenever we have a double bond, one bond is sigma, the second one is pi, therefore this carbon over here must be sp2 hybridized, having three sp2 hybrid orbitals, two of them to binding hydrogens, a third one to bind this carbon, and the fourth orbital is a pure p for the pi bond. Same thing applies for the carbon next to it. This is an sp2 hybridized carbon for the same reasons. Three hybrid sp2 orbitals, one to bind this carbon, another one to bind this carbon, a third to bind a hydrogen, and the fourth orbital is a pure p orbital for the pi bond over here. The next carbon here, as you can see, is a carbon with four single bonds. One bond to this carbon, one bond to this carbon, and two bonds to two hydrogens that we don't need to show. Therefore, the carbon must be sp3 hybridized. The next carbon over here is a carbon also that has a double bond. Now we know that that's an sp2 hybridized carbon. Same thing applies to the next one to it. Same thing to the next one over here. And same thing to the next one over here. All this carbon must be sp2 because they have a double bond next to it. So then we have the nitrogen atom. The nitrogen atom, first thing we need to do is to complete which I should have done before, the Lewis structure, I'm going to add the lone pairs. And I know now, and as I said in class, any atom with lone pairs next to an sp2 hybridized carbon will also be sp2 hybridized. Guys, I want to emphasize this. You will find in a lot of videos out there, okay, huge mistakes in regarding to the hybridization of case like this. Even in the clutch prep website, there might be some videos, I haven't looked at all of them, in which they use the wrong language. So watch out for that. The problems are all okay because I made sure that every explanation in the problems is correct. I'm not checking the videos, but regardless of where you search for information, make sure that you look for the right information, okay? Any atom with lone pairs next to an sp2 hybridized carbon would also be sp2 hybridized, all right? And now we have this carbon over here. This carbon over here has 4 single bonds, 1 bond to this carbon, 1 bond to this carbon, and 2 hydrogens we don't need to show. So obviously that is sp3 hybridized carbon. And the next one over here is a carbocation. And now we know that any carbocation is also an sp2 hybridized carbon. So remember, carbocations, carbon ions, and radicals will be considered sp2 hybridized carbon. This could be the distribution of an sp2 hybridized carbon, 3 sp2 hybrid orbitals, okay, and a perpendicular p orbital, which will be used for a pi bond if there is a double bond, or which is empty if it is a carbocation, okay? So now that we have assigned hybridization to every single atom in the molecule, we can move on and then ask the following question. Is this a delocalized system? So to answer that question, we're going to look for 3 or more sp2 atoms next to each other and properly aligned. Okay? That's going to be the criteria to determine if the system is delocalized or not. 3 or more sp2 atoms next to each other and properly aligned. That's why we also have to assign first hybridization. When I look at my molecule, I can see over here I have 2 sp2 carbon, the next one is sp3, so this is only 2, therefore there is no delocalization over here. If I look in the next section of the molecule, I see a double bond here. Up here you see another sp3, no delocalization toward this side. When I look toward the other side, obviously I have 1, 2, 3, 4, 5 sp2 atoms next to one another, so there is a quite extensive delocalization over here. From here to here, we see how this carbon atom is sp3, no delocalizations toward this side, and here this is another sp2, therefore the delocalization is even extensive toward this area. Okay, so my next and last point here to answer, to draw the resonance structure properly will be now, it will be to draw the, make a drawing draw the delocalized area, the area where electrons are delocalized. And remember, we're talking about pi electrons, obviously, okay? And that is important because knowing the area where the pi electrons are delocalized will help you to understand how many resonance structures do you need to draw, okay, to account for such delocalization. When I remove double bonds, so I can tell that if I has, so the answer to this question, what is the area where the p electrons will be delocalized? Whenever you have consecutive sp2 atoms next to each other, properly aligned. So I see 1, 2, 3, 4, 5, 6 consecutive sp2 atoms next to one another. Therefore, okay, therefore, the delocalization that I'm going to show by the means of resonance theory should account for delocalization throughout this entire area of the molecule. Basically, over here. So I'm going to draw it like this. This area, there is delocalization here. There is delocalization over here. Next, there is delocalization too. In the next bond, there is also, that's an area of delocalization. And also in the carbon-nitrogen bond. So once we know the entire area where, where we will find delocalized by electrons, then our resonance structures should or must account for that area. So I know that the entire section of the molecule over here will have pi electrons delocalized. Why is that? Because once again, this is an area where we have sp2 atoms next to each other and properly aligned. So with that in mind, we can then go ahead and start drawing our resonance structures. Okay? So if we're going to draw resonance structure, the first thing we're going to do is to introduce the brackets. Okay. This is another molecule that I have here for a second example, so don't worry about that now. And I'm going to place my first double-headed arrow. Remember now, the next step is going to be how to use curved arrows to show the flow of pi electrons from one resonance structure to the next. That is the second big thing to be learned here in resonance theory. We know that the arrows can only depart from source of electrons. Source of electrons in this case are only double or triple bonds and lone pairs, because in resonance structures only the pi electrons are flowing. So I have a carbocation here with an empty mp2 with an empty p orbital next to a double bond, so I can clearly flow the electrons from the double bond over here. Okay, that will create a new structure. Okay, in that new structure, I am basically moving the double bond over here. And if I do that now, clearly, as is indicated, so once again, guys, in the arrow is departing from wherever the electron source is. In this case, is the double bond. And the arrow is ending wherever this new bond is going to be formed. In this case, this arrow is indicating that there's going to be a pi bond in between these two carbons right over here. If we do that, this carbon will be left with 3 bonds, and therefore it will be positively charged. Remember, the charge in every single resonance structure will always be the same. If here the net charge is +1, here it also must be +1. So I'm going to copy this structure. I'm going to paste. Now we're going to flow for the next structure. So once again, here we have a pi bond next to a charge, so we can easily see how these pi electrons can be moved to the next carbon, creating now a double bond over here. And if I do that, then obviously this carbon will be left with 3 bonds, and it will be positively charged. Okay. And now next to it, I also have an sp2 hybridized carbon atom is a nitrogen with a lone pair, which is obviously can contribute to stabilize this charge. So the lone pair can actually make double bond over here. And in that case, this is a double bond will be formed with a nitrogen. Now the lone pair is gone because I have 2 hydrogens in that nitrogen. That hydrogen must be now a hydrogen with 4 bonds, must be positively charged. Okay. Now, as I said, there is no more resonance structure because the carbon, okay, the carbon next to here is sp3 hybridized, no delocalization toward this side, so that's it. So if you see the flow of electrons is happening through the area where we have all the sp2 atoms next to one another and properly aligned. So these could be the 4 resonance contributors to the hybrid of this carbocation. I want to emphasize something else. You will find in a lot of videos and even in some textbooks, people talking about stability of resonance structures. And I'm going to write it over here. Resonance structures cannot be stable because simply they don't exist. And this is very important, okay? So the language is very, very important. I want you guys to, so we refer to, and instead, we refer to energy. So we rather refer to, and I'm going to rewrite it over here because this is also widely used out there and people use it wrong. So we refer to energy of resonance contributors or the structures. Okay, so if we're going to compare the energy of the resonance contributors, we can determine which of these structure contribute the most to the hybrid. And for that, we learn a set of priority rules. In those priority rules, we learn that the number 1 rules was atoms having a full octet. As you can see in the first 3 structures, the carbon has only 6 electrons in the valence shell. That's why it's a carbocation here, here, and here. In the 4th structure, even though the positive charge is on the nitrogen, all atoms, including nitrogen and carbon, has a full octet. That's the number 1 priority rule. So that makes this structure over here to be the highest contributing structure of the hybrid. Okay, so I'm gonna say over here, this is the highest contributor to the hybrid. We don't say, once again, never say this is the most stable. None of these structures in reality exist. Okay, this is simply the most significant contributor to the hybrid, which basically means that the hybrid resembles this structure the most. So in the real structure of this carbocation that I show here, we can say that and this is important now, okay? So this is how we draw the resonance structures. So now next we look at how can we interpret this data. So what resonance theory is telling me is, in this carbocation, which is only one, the positive charge is shared in between this carbon, this carbon, this carbon, and the nitrogen. So in the hybrid, in the real hybrid, which I'm gonna show because I'm gonna try to read over here. In the real hybrid, there's gonna be a partial positive charge over here, partial positive charge over here, over this carbon here, okay? There is gonna be also a partial positive charge over this carbon, and also over the nitrogen. Obviously, the nitrogen has a full octet, okay? Whereas the carbon has only 6 electrons in the valence shell. So if there is going to be a reaction, this could be the center of reaction. So this carbocation will be reacting with a negative species, let's say A minus, because once again it's a carbocation, okay? It's electron deficient, therefore it will react with species that are rich in electrons. I'm gonna show, for example, one here. And if one species that is rich in electrons reacts with its carbocation, it will react either here, here, or here, because those are the 3 carbon atoms that share the electron deficiency. Okay, it cannot react on the nitrogen because the nitrogen has already 4 bonds. There is no empty orbitals to receive any electrons. Okay, just keep that clear. So the real structure resembles this the most. However, these 3 contribute significantly, and that actually explains why there is electron deficiency that is shared between this carbon, and this carbon. And that is used to make a prediction that if a negatively charged species were to react with its carbocation, it will attack this position, or this position over here, because those are the 3 carbons that have share the electron deficiency and having only 6 electrons in the valence shell. Okay, so to solve this problem, I want you guys to follow this step whenever you see a resonance problem. First of all, find out if the system is a delocalized system. To answer that question, assign hybridization to every atom, looking for either pi bonds or atoms with lone pairs next to pi bonds. If you have 3 or more sp2 atoms next to one another and properly aligned, the system will be delocalized. Then you must understand the area where the electrons are delocalized in the molecular ion. Once you know that, you will understand how many resonance structures you should draw. Using the curved arrow symbolism, you flow the pi electrons one at a time, creating all the possible resonance structures that are actually showing how the positive charge is shared. And finally, you can determine which is the most significant contributor, meaning that the hybrid will resemble more this structure based on the priority rules. And also, you can interpret out of this hybrid where and how this carbocation will react. Carbocations are electron deficient species. Carbons having 6 electrons in the valence shell, they will react with electron-rich species. So if an electron-rich species approaches this carbocation, it will be attacking basically this carbon, this one, or this one, because those are the 3 positions that share the electron deficiency. Note that even though this carbon is sp2 hybridized and this carbon is sp2 hybridized, they do not share the electron deficiency. That's why and an ion will never attack neither of them. Okay, so that's how you guys have to approach every single resonance problem.